Hello everyone, welcome to module 8. So in this module we're going to talk about thermochemistry, so which deals with entropy, free energy and the direction of chemical reactions. So let's start with the common outline. So in this chapter we're going to talk about the second law of thermodynamics and which predicts the spontaneous change, how to calculate entropy change of a reaction, and entropy, free energy and work. Finally, free energy, equilibrium and reaction direction. So let's start with what is a spontaneous change. So a spontaneous change is something that occurs without continuous input of energy from the outside of a system. So all general chemical processes require energy but to take place, but once you start a spontaneous process, so there is no requirement of input of further amount of energy. So oppositely, a non-spontaneous energy change occurs only if the surroundings continuously supply energy to the system. If a change is spontaneous in one direction, so it will be non-spontaneous in the reverse direction. So let's look at something that cannot predict a spontaneous change. So the first law of thermodynamics cannot predict spontaneous change. So we know that the first law basically says that the energy is conserved, so it's neither created nor destroyed, but is transferred from heat to work or work to heat. So delta E equals Q plus W. So the total energy of the universe is going to be delta E of the system, which is going to be minus delta E of the surroundings, or delta E of the system plus delta E of the surroundings equals delta E of the universe, which should be equal to 0. Now the law of conservation of energy applies to all changes, so and does not allow us to predict the direction of a spontaneous change. Next, what does not predict? The next one that cannot predict is the enthalpy change. So the enthalpy change cannot predict the spontaneous change. So the amount of enthalpy here, the spontaneous change can be exothermic or endothermic. For example, spontaneous exothermic processes include freezing, condensation at low temperatures, combustion reactions, oxidation of iron and other metals. Spontaneous endothermic processes include melting and vaporization at high temperatures, dissolving of most soluble salts. So the sign of delta H is not a good predictor of spontaneous change. So what is the next thing that can predict it? Next, let's talk about freedom of particle motion. So we know that all spontaneous endothermic processes result in an increase in the freedom of the motion of the particles of the system. For example, we have a solid and increasing the number of the freedom of the particles, converting it to a liquid, thereby again increasing it by converting it into a gas. So again, when you have a crystalline solid plus liquid, it becomes ion in the solution. So you start from a less freedom of energy motion to more freedom of particle motion, and localized energy of motion to a dispersed energy of motion. So a change in the freedom of motion of the particles in a system is a key factor in affecting the direction of the spontaneous change. So the spontaneous change always tries to go towards the one that has more degrees of freedom. So let's talk about degrees of freedom right now. So just as the electronic energy levels within an atom are quantized, a system of particles also have different allowed energy states. So each quantized energy state for a system of particles, we call it a microstate. So at any instant, the total energy of the system is dispersed throughout the one microstate. Now, at a given set of conditions, each microstate has the same total energy as any other. So therefore, they are equally likely. The larger the number of possible microstates, the larger the number of ways in which a system can disperse its energy. So why do we need to talk about microstates? So microstates can help us understand entropy. The number of microstates in a system is related to the entropy of the system. So which can be written as S equals K times ln W. So a system with fewer microstates will have lower entropy. A system with more microstates has higher entropy. So therefore, all spontaneous endothermic processes exhibit an increase in entropy. So entropy, like enthalpy, is a state function. So therefore, it is independent of the path taken between the final and initial state. So we can say that the delta S is S of minus Si. So let's take an example of a spontaneous expansion of a gas. Let's say we have 1 mole of gas on one side, which is completely filled, and another side which is evacuated. Now once you open this valve, what you're doing basically is that you're letting the air pass through it, Now the air will continuously expand until the point where both their moles become equal. So both the amount of gas in both of them becomes equal. This is an expansion process which is spontaneous because there is no requirement of energy for this process to start. So you don't need to push the gas from this vessel into this vessel because the gas directly or freely moves from one vessel to the other vessel. So increasing the volume increases the number of translational energy levels that particles occupy. Therefore, the number of microstates and the entropy will start increasing. So we started with a certain number of energy levels. Now when you open the cock, you open the stopcock, you are basically increasing the number of microstates, thereby increasing the entropy. So what are the possible states in which we can think of the number of microstates? So here we have two particular states at which we are starting. So we can say that this has a 2 power n number of microstates, where n is the number of particles. So let's say, for example, if we start with one particle, so that gives you 2 power 1, where the A particle can be in the first vessel or the second vessel. If you have two particles, there are 4 combinations that you can get. You can have AB, A and B in different vessels, B and A in different vessels, and BA in the second vessel. If you have 3 different particles, we are basically increasing that to 2 to the power 3, which is going to be 8. If you have 10 atoms, that gives you 2 power 10. If you have Avogadro number of atoms, that gives you 2 to the power Na. So which gives you 2 to the power 6 times 10 to the power 23, which is a high value, which is the idea behind the topic of microstates and understanding how entropy can be calculated. So now let's talk about how to calculate the entropy for a reversible process. So the change in entropy of the system is the reverse amount of energy over time. So a reversible process is one that maintains such tiny increments that the system remains at equilibrium, and the direction of change can be reversed by infinitesimal reversal of conditions. So how do you think about it? Let's say, for example, we have a process where we are compressing gas by pouring sand. Now we started the process in one direction. We have to go back in the same path, so which means that now we are going to remove each speck of sand one by one, resulting in an infinitesimal decrease in the pressure, therefore causing the gas to expand a really tiny amount, therefore resulting in a reversible process. So this is what we call as a quasi-static process. So it's not completely reversible, but it's quasi-reversible or quasi-static process. Next, let's talk about the second law of thermodynamics. So we saw that the sign of delta S for a reaction does not by itself predict the direction of a spontaneous reaction. Now, if we consider the system and the surroundings, then we find that all real processes occur spontaneously in the direction that increases the entropy of the universe. So which means that for a process to be spontaneous, there has to be a decrease in the entropy of the system that must be offset by a larger increase in the entropy of the surrounding. So let's look at it this way. So the change in entropy of the universe requires the change in entropy of the system plus the change in entropy of the surroundings, so which should be greater than 0. So which means for this to be greater than 0, delta S of the system must be in such a way that there is a decrease in the delta S of the system and resultant increase in the delta S of the surroundings, which results in the final understanding of how to look at spontaneous change. Now, comparing energy and entropy. So we know that the total energy of the universe remains constant. So we generally approximate it by using delta H. So for enthalpy, there is no net point. So we always measure the changes in enthalpy. The total entropy always increases. So which means delta S of the universe always has to be greater than 0. So for entropy, there is a 0 point and we can determine the absolute entropy value. So that's the only difference between enthalpy and entropy. For enthalpy, there is no 0 point. Therefore, the change is the one that we generally look at. For entropy, there is a 0 point. That's why we determine the absolute entropy values. Now, a perfect crystal has 0 entropy at absolute 0. This is generally called as the third law of thermodynamics. So a perfect crystal generally will have 0 entropy at 0 Kelvin. Now, a perfect crystal generally has flawless alignment of all its particles at absolute 0. The particles will have minimum energy, so there is only one microstate. So when the microstates equals 1, S equals 0. Now, this generally is not possible in nature because you cannot have flawless alignment of particles. There will always be some irregularity. That's why achieving 0 Kelvin is not possible. So, which means that achieving 0 entropy is also not possible. Next, let's talk about S prime. So, which is generally called as the standard molar enthalpy, molar entropy of a substance. So, it generally measured in its standard state in the units of joule per mole Kelvin. So, the conventions used for a standard state include 1 atmosphere for gases, we use 1 molar for solutions, and the pure substance in its most stable form for solids and liquids. Now, what are the factors that affect entropy? So, entropy generally depends on temperature. So, which means that increase in temperature causes an increase in the molar entropy. Entropy also depends on the physical state of substance. So, phase changes from solid to liquid and liquid to gas increase the entropy. The formation of a solution also affects entropy. And finally, entropy is related to the atomic size and molecular complexity. So, remember to compare substances in the same physical state. So, the lesser the freedom of motion, the lower the temperature, the lesser the freedom of motion. The lesser the freedom of motion, the fewer the microstates, therefore will have lower entropy. When you increase the temperature, you're basically putting up more heat, causing it to have higher temperature, which results in more freedom of motion, which again results in more microstates, therefore resulting in higher entropy. So the lower the temperature, fewer microstates and lower entropy. Higher the temperature, the more the microstates, higher the entropy. Next, let's look at phase change. So phase change causes what we call the freedom of motion. So particles generally are fixed to 1 or 2 microstates when they are at a solid position. That changes rapidly when it becomes a liquid, and that liquid becomes much more free when it becomes a gas, therefore resulting in higher and higher entropy as you go from a solid into a liquid and from a liquid into a gas, resulting in an increase of entropy. So again, next let's take a look at the entropy of dissolution of a salt, basically a solutions. So when you take a pure solid and pure liquid, and when you take a pure solid, which is the salt, and mix it together with a pure liquid, you are basically changing the particles' chances of motion and the type of motion that it can have. So which means that there's a greater number of microstates that can happen. So the entropy of a salt solution generally will be greater than that of a solid or water, because it is affected by the organization of water molecules around each ion. So that disturbance increases the entropy. Next, entropy when you have a gas dissolved in a liquid. So entropy of a gas is already so high that it decreases when the gas is dissolved. So which means that this is one case where you might see actual reduction in the entropy in comparison to both the reactants and the product. Next, let's take a look at entropy and atomic size. So the entropy is higher for larger atoms or molecules of the same type. For example, let's take the example of the first group 1A group of elements. So you have lithium, sodium, potassium, rubidium and cesium. Now notice that the atomic radius starts increasing, and also notice that the entropy also starts increasing rapidly. The main reason is because of the fact that the larger the molecule, the more unstable it is, resulting in a higher entropy, causing it to have more freedom, causing it to have more microstates, resulting in a higher entropy. So therefore, molecules that have similar characteristics, molecules of the same type, generally will have a higher entropy for larger atoms. For allotropes are generally different versions of the same material. The entropy is higher in the form that allows the atoms have more freedom of motion. For example, you start taking NaCl and compare it with AlCl3. Notice that it starts with 72.1 and you start increasing to 167 because there is more freedom of motion, because you have NaCl, which is just one bond, where the vibration is only for one bond. But when you take AlCl3, you have 3 different chlorine molecules that are bonded, which means that there is more freedom and more vibrations, which results in a higher entropy. So the more complex the molecule, the higher the entropy. So these trends only hold for the substance in the same physical state. So this is an important point to remember. Again, you can take comparison between graphite and diamond. So the one graphite, notice that graphite is a much more lenient structure, much more free structure, which has a higher entropy. but diamond, which is a more constricted structure, where restricted structure, which results in a lower entropy. So this is one of the reasons why you can see the differences between nitrous oxide, nitrogen dioxide, and nitrogen dinitrogen tetroxide. The main reason why they have different entropies. So use the same principle now. Pause the video right here and try to answer the following questions. Next, let's talk about entropy changes in the system. So the standard entropy of reaction, which is delta S of the reaction, is the entropy change that occurs when all the reactants and all the products are in their standard states. So the delta S of the reaction is sigma of the products minus sigma of the reactants of the entropies, where M and N are the amounts of products and reactants given by the coefficients in their balanced equation. So predicting the sign of delta S of the reaction. So we can often predict the sign of delta S of the reaction for processes that involve a change in the number of moles of a gas. So delta S is going to be positive if the amount of gas increases. For example, we start with a gas and a solid. We start noticing that now both of them are gases, so which means that there is a positive change in the entropy. Now, delta S of the reaction is negative if the amount of gas decreases. Notice that now we have two gases becoming one single gas, which means that there is a reduction in entropy. So delta S is likely to be positive if a new structure forms that has more freedom of motion. Now notice that we have a constricted structure which results in a freer structure after producing some heat. So which means that delta S is going to be likely to be positive if there is a new structure that forms that has more freedom of motion. So let's take an example right here. So predict the sign of delta S of the reaction and calculate its value for the combustion of 1 mole of propane at 25 degrees centigrade. So let's take the values right now. So this is the equation right here. So you have C3H8 plus 5O2 gives you 3CO2 plus 4H2O. So 3CO2 plus 4H2O. Now we know that delta S of the reaction is sigma M times S of the product reactants. So notice that M times S of the products minus sigma N times S of the reactants. So notice that this is the products. So the value is going to be 3 times S of CO2 plus 4 times S of H2O minus of S of C3H8 plus 5 times S of O2. So these values, when you substitute those values, so 3 times S of CO2 is 213.7 plus 4 times S of H2O is 69.9. So this is the product part minus of S of C3H8 is 269.9 plus 5 times S of O2 is 205.0. So these values are generally taken from the table at the end of the textbook. So the final answer gives you a value of minus 374 joule per Kelvin. So delta S of the reaction. Notice that the delta S of the reaction is negative. The main reason here is because we have two gases converting into one gas and one liquid. So notice that we are reducing the phase as well as converting a phase change, which means that there is a resultant decrease in the number of microstates possible. So which means that there is a decrease in the total entropy. So delta S is going to be negative. Now let's talk about entropy changes in the surroundings. So a decrease in entropy of the system is outweighed by an increase in the entropy of the surrounding. So which means that if the delta S of the system decreases, there is a proportional delta S of the surroundings increase. Now the surroundings function generally as a heat source or heat sink. So in an exothermic process, the surroundings absorb the heat released by the system. Therefore, the entropy of the surroundings will increase. So generally Q of the system is less than 0, Q of the surroundings is greater than 0, and delta S of the surroundings becomes greater than 0. Now in an endothermic process, the surroundings will provide the heat absorbed by the system. Therefore, the entropy of the surroundings decreases. So Q of the system is greater than 0, Q of the surroundings is less than 0. Therefore, delta S of the surroundings is less than 0. Now, let's talk about the temperature at which heat is transferred. So since entropy depends on temperature, so delta S of the surroundings is generally affected by the temperature at which the heat is transferred. For any reaction, remember that Q of the system is equals minus Q of the surroundings. So the heat transferred is specific for the reaction and is the same regardless of the temperature of the surroundings. Now the impact on the surroundings is larger when the surroundings are at a lower temperature, because there is a great relative change in the entropy of the surroundings. So the entropy of the surroundings can be written as minus Q of the system over T. So when you have a process at constant pressure, so we don't need to take the Q of the system. So Q equals delta H. So which becomes minus delta H of the system by temperature. So this is the formula for delta S of the surroundings. So in the next lecture, we will try to solve some problems regarding